So for example, in this first question, we have these halogenoalkanes reacting with hydroxide ions to give you alcohol and a halide. This is your classic hydrolysis reaction. So hydrolysis is the type of the reaction, but in essence, you can also call it nucleophilic substitution. That is the mechanism in which how it proceeds. All right. So we know that rate of this type of nucleophilic substitution can be SN1 and SN2. So SN1 versus SN2. You can brush up your theory if you wish to by going through the topical playlist under halogenoalkanes, where there's a lot of questions on SN1 and SN2 from structured papers, of which they can come from experimental results such as these. They could also ask you under rate of reaction, such as the A2 component of reaction kinetics or rate of reactions, where they will have some data on initial rate of reaction, some graphical data on like concentration on time, and then you can work out order of reaction. Okay, so the rate at which the reaction occurs depends on which of the halogenoalkane is chosen. So it is a nucleophilic attack, as I mentioned, and the rate might depend on the polarity, which all the halogens are electronegative, more electronegative than carbon. So if I have my simple electronegativity scale, I have, what do I have? I have chlorobromoiodine. So I have chlorobromoiodine. So chlorine, bromine, iodine, and then carbon will be there. And it also depends on the bond strength, so the energy of the carbon halogen. You're not given data booklet in paper 5, so you need to appreciate that going down the group from chlorine to bromine to iodine, the halogen atom gets bigger. Therefore, the carbon bonded to the halogen, which gets bigger, the bond will get longer, and longer covalent bond would mean weaker covalent bond because you have weaker electrostatic force attraction between your electrons that are used for covalent bonding and the two positive nuclei. That is your definition of covalent bond, right? The electrostatic force attraction between the bonding electrons and the two positive nuclei. So the further this nuclei is, due to the bigger size of the atom, then the longer the bond, the weaker the bond, the weaker the covalent bond. Okay. Polarity is to do with electronegativity. Electronegativity is defined as the ability or the property or the power of an atom. So it's to do with an atom, it's not to do with a molecule. Okay. And we have this delta minus to represent that the electrons in the covalent bonds are not shared equally. Instead, they are polarized towards the more electronegative element. They lie closer to the slightly more electronegative element. Okay. So the bigger the difference, the more polar is the bond. Like carbon and iodine, the difference is smaller than this. Therefore, carbon iodine is less polar than carbon chlorine, for example. Now, in the first question, they say if the rate of reaction was only controlled by polarity, which should be most reactive? If this is the only factor, then the more delta negative the halogen atom is, then this will make the carbon more delta positive, and this will make the hydroxide, because you have an attack by hydroxide. The negative charge is on the oxygen, but the nucleophilic attack means you have a lone pair on the oxygen. They will attack the carbon. So the more delta positive the carbon, as a result of the more electronegative halogen, as a result of bigger electronegativity difference between the carbon and the halogen atom, then the more delta positive this is, the more this one will be attracted to attack this one. Okay, so the most reactive, we will expect it to be the one where the difference is the biggest. So that will be the chlorobutane. They say most reactive to least reactive, so I have to write down all the order because they say consider all these three only. All right, so bromoethane and iodobutane. Did I say ethane? Okay, it is butane, all right. In terms of the polarity, all right, so down group 17, the electronegativity of the halogen increases, so they become more and more electronegative. Therefore, the difference in electronegativity, or you talk about electronegativity difference between carbon and the halogen decreases, because down the group, so you can see down the group, the difference gets smaller and smaller, so that gets decreases. Therefore, carbon halogen, maybe I just say let halogen be X. Let halogen be X. So carbon halogen bond becomes less polar. Carbon less delta positive. Therefore, hydroxide ions which are negatively charged. So bracket negatively charged are attracted to the carbon delta plus lesser, or you can say the hydroxide ion which are negatively charged are less attracted to the carbon delta plus. I mean, it's the same thing really, it's just a rearrangement of your comparative adjective, yeah? I don't know, comparative adjective? Well, I don't know, I'm not an English teacher, you can ask your English teacher, but that sentence to me looks alright, or you could have put a lesser there, okay? If, however, if the rate of reaction was only controlled by the bond strength, so if this is the only factor that controls it, remember there are two potential factors that could control it. If it depends on bond strength, then which one is the most reactive? The most reactive one would be the one where it's the easiest to break the carbon halogen bond. That means when the carbon halogen bond is the weakest, that means it's going down the group is most reactive. Okay, if it is based on bond energy. Because if I have a simple scale, that is your energy of your carbon halogen. So your CCl will be stronger than CBr, than your Ci, because going down the group, the halogen gets bigger, right? So down group 17, halogen gets bigger in size because they have more field size or atomic radius. They're saying the same thing, okay? I should probably have more space in between. So what happened is halogen gets bigger due to more electronic shells, due to more field inner electronic shells, something you would be accustomed to doing when you explain your group 2 essays on solubilities of the sulfate, the hydroxide, the thermal stability of their carbonates, their nitrates, similar kind of thing, right? So it gets bigger in size, therefore, or hence, maybe I just use hence. Now I just use a shorthand notation. Therefore, a carbon halogen bond gets longer, and hence weaker covalent bond. Weaker covalent bond, CX, will break more easily. Therefore, Ci will react the fastest. So the iodobutane would be expected to be more reactive than the bromobutane, than the chlorobutane, if we are just basing the reaction, the rate of reaction, based on bond strength. But I hope immediately you can see that these two things, if you base on polarity versus if you base on bond strength, they give you opposite trend. So this investigation really is about which one is more relevant. Which one is more relevant? So that is your hypothesis based on the two different factors. They give you different results. So now you go into the lab. Well, someone go into the lab. All right. Preferably is you, because they give you all this information, right? So imagine you doing it, and then you carry out an experiment to compare the extent of the reaction. So you react the different halogen alkanes with your hydroxide ions. You take it out to react with sodium hydroxide for 2 minutes at 50 degrees Celsius. This is probably to make the reaction more rapid. After you react with sodium hydroxide for 2 minutes, then you add silver nitrate So Ag plus NO3, it's aqueous, so it's a colorless solution. If you use it before, you know it's a colorless solution. But then you get a silver halide precipitate because Ag plus aqueous plus a halide ion will give you AgX solid. This is the common ionic equation. They love to ask you to write even back in GCSE or IGCSE or O-level as a type of precipitation reaction. So all chlorides are soluble except for silver chloride and lead 2 chloride. They are white in color. All iodides are soluble except for silver iodide and lead 2 iodide. They are yellow in color, etc. etc. Alright? Some hazards associated with the use include very hazardous when you have skin and eye contact. So obviously you will have safety goggles on, so you wouldn't necessarily have it gone into your eye. But in terms of skin, so we can think about chemical resistant glove. Very hazardous if inhaled or ingested. I wouldn't worry about ingested because you don't eat the chemicals, do you? Okay. But in terms of inhalation, you might breathe it in, so you might want to consider doing it in a fume cupboard because a fume cupboard has a ventilation that sucks up all the whatever volatile stuff that's toxic, sucks it up through the ventilation. And last thing, flammable means it catches on fire, so you need to keep it away, keep those chemicals away from all the halogen alkanes, keep them away from naked flame or naked fire, yeah? Well, or fire, naked flame is fire, alright? So carry out this experiment, you have these following things, you have apparatus, you have reagents, including solution of sodium hydroxide and silver nitrate. You have a sample of these 3 different liquid halogen alkane. So what are you going to change and what are you going to measure? Okay, so we are trying to get the formation of the silver halide precipitate. We want to see how fast does it take for the silver halide precipitate to form as well, right? Let's see. Actually, there are 2 ways of doing these experiments, because one is you could change. We are definitely changing the chloro to bromo to iodose, so that is definitely what is changing. So y-axis is the dependent, that is what you measure. Independent variable is the x-axis, it is what you change, alright? So it's what you change. So if you watch my other tutorial videos on paper 5, so why are you so dependent, right? So, you know, y-axis, dependent variable, okay? So we are changing the type of the halogenal alkane. So that one is for sure. So we are changing it from chloroalkane to bromoalkane to iodoalkane. So what are we exactly measuring? If I go further, this is about rate, right? But remember that all of these, you see, you are stopping it after 2 minutes. You are stopping it after 2 minutes, okay? All of it, you stop it after 2 minutes. So you are not changing the time, okay? I was a bit dubious about this because what happened is in a different variation of this experiment, you would just add the silver nitrate together with the halogenal alkanes, and then you record the time taken for the precipitate to form. Alright? Obviously, like the weaker the bond, the longer it will take for you to detect the first hint of precipitate. That will come from the most reactive halogenal alkane will produce the precipitate the fastest, and the least reactive halogenal alkane, okay, meaning it will be the slowest. It will give you the precipitate for after a much longer time. So what we have here really is we just stop the reaction after 2 minutes. After we heat it up, we just add aqueous silver nitrate, we get silver halide precipitate. So we are not monitoring the time taken for the silver halide precipitate to form. Instead, we're gonna collect how much silver halide we form after a specific time. So this is a fixed time, and we measure how much precipitate is formed. Whereas the other variation I was talking about is it will give you a fixed amount of precipitate, and then I monitor the time taken for it to form a fixed amount of precipitate. Okay, so there are two variations: fixed amount of mass of precipitate. What is the time? So that's what you measure, versus fixed time. Then what is the amount of your precipitate? Okay, there are two different variations of experiment. Okay, obviously you can monitor time, or you can monitor the amount of halide solid that you form. They can filter off and work out what's the mass, right? So I think in this experiment we are going for the first one here instead of this one. So this is the mass or the amount, of the precipitate, which is the silver halide formed after a fixed time. Alright? So the amount of each halogen alkane used is most practically measured by its volume. Okay, because they are all liquids, by the way. They are all liquids. So usually you will use equal volumes. Alright? But why is this not ideal? As you know, density equal to mass over volume. If you use the same volume, it is not the same mass, it is not the same mole. Alright? So what should be changed? What should be changed to obtain a more reliable comparison? So usually we use the same volume, but that would mean same mole, as I mentioned. So what we would do is we would try to work out to use the same mole of the halogen alkane, so we can have a fair comparison. This is called fair testing, and it's something that you would have done when you first started doing any experiments. They call them fair testing. Yeah. So here, equal volumes of the three halogen alkane does not mean equal masses. Based on what I just said, okay, because they can have different density. Densities is mass over volume, right? Okay. Therefore, since they are not the same mass, they will not give you the same mole. Therefore, not the same mole. Okay, so mole is amount, mass is mass. Okay, so we can set out to use the same mole quantity for all three halogen alkane. So if you want to use the same mole, then you can calculate mass required for each, then use densities, or otherwise, or if you just measure the mass in a test tube or something, or otherwise to measure out the required volume, Okay. So next bit is about the experiment again. So having measured the quantity, so you now know how much you need. What must be ensured about the amount of sodium hydroxide used? All right. So that is not what we are changing. We want to make sure that they are the same throughout your whole different experiment. So we have to use the same amount of the sodium hydroxide each time. Because if you use a different amount of sodium hydroxide each time, then you're not doing a fair testing. Yeah, aqueous for all three halogen alkane. So this is one of the things that can change. They can affect the reaction, what you're trying to monitor. So you want to keep it constant. So this is one of those control variable. All right. Remember earlier they say it was at 50 degrees Celsius. If you forget about it, you should have read the question earlier. It says you did it at 50 degrees Celsius for 2 minutes, alright? The thing is, how can you ensure that it is heated up to 50 degrees Celsius? And how do you start the experiment? So there's 1 and there's 2. So there's quite a lot of lines here. We can use a thermostatic water bath, because a thermostatic water bath, you can adjust the temperature and it will not go above it because it's controlled by thermostat. Set at 50 degrees Celsius to heat the reaction tubes. Okay, to heat the reaction tubes and maintain that temperature, because like I said, if you use a normal water bath on the Bunsen burner, okay, like basically you have a beaker supported on the Bunsen burner, that can continue heating up and the temperature will not be maintained, yeah? Whereas a thermostatic water bath maintain the actual temperature at 50 degrees Celsius, and that is essentially better, okay? How can we start the experiment? So we want to mix the hydroxide. Hang on, what reagent could we add that which will ensure that after 2 minutes the reaction will stop? So you see, this and this are heated at 50 degrees Celsius. That you don't mix them first, alright? You heat them separately at 50 degrees Celsius, then you react them together and then you start counting for 2 minutes, alright? To heat the reaction tubes and aqueous NaOH, okay, and maintain the temperature. Then mix the hydroxide and the halogenoalkane together, both having been heated to 50 degrees Celsius, and start timing immediately. For 2 minutes, because you only want the reaction to last until 2 minutes, yeah? Okay, from the moment of your mixing, alright? So what reagent could we add to ensure that we stop the reaction? What was the reaction? You have a hydroxide, you have a halogenoalkane. Now you also, you haven't added the silver nitrate yet. So this thing can react. This is your nucleophile. It attacks the carbon halogen bond, okay? It attacks the carbon atom actually, and it breaks the carbon halogen bond. So we can be thinking about removing this. When you remove the hydroxide, you remove the reactant, one of the reactant, and there will be no more hydrolysis, alright? So what we can do to remove OH minus is we can add acid, okay? But then you have different acid to choose from, NO3, H2SO4, etc., etc. But the one acid that you should not use, especially in the context of halogenoalkane, where X could be chlorine, bromine, or iodine. And remember, your product is actually ROH and X minus. If you put in HCl, then you are introducing Cl minus, and you will have more silver chloride precipitate. So that is a no for this particular reaction. But HNO3 would have been alright, because all nitrate is soluble. You are using silver nitrate, so you're not exactly precipitating out any nitrate at all. In terms of sulfate, is also a bit ambiguous, because silver sulfate, I don't know actually solubility of silver sulfate, but I know that silver nitrate are soluble because that was what I used for my silver reagent, silver nitrates. All nitrates are soluble, so I'll be more comfortable using things like HNO3 in this particular reaction to neutralize the hydroxide, which is the reactant. So if you remove one of the reactant, there will be no more reaction. Okay, so but then you want to ensure that it is stopped. So you want to add excess, okay? because if you don't add excess of the acid, you might still have some of these and the reaction might still continue. So next bit, after the reaction has been stopped and you add in the aqueous silver nitrate, so you add excess HNO3 already, so no more hydroxide, the reaction has been stopped, you add in silver nitrate, you get precipitate. And how much precipitate, so the amount meaning the mole, how much precipitate you get could be determined by measuring its height. So you have this test tube which has the OH minus plus RX giving you the X minus plus ROH, and it is this X minus that, you know, when you add in the drop by drop of the silver nitrate aqueous, then what happens is this thing will start to precipitate out, especially where the silver nitrate come into contact with the halide ion, so it will give you silver halide precipitate. You will see how high the height of the precipitate form, okay? But importantly, you need to leave it for some time before making the measurement on the height. If you measure the height straight away, the reaction could still be going on, and as you know, you are dropping it on the surface, so your precipitate start forming on the surface, but the precipitate is heavier, so they will eventually sink to the bottom, but it might take some time. All right, so initially some precipitate, some of the silver halide AgX precipitate, so Ag plus X minus because it's group 17 halide, might only form at the surface. At the surface where silver nitrate aqueous comes into contact with the solution mixture. So wait for precipitate to settle to the bottom, to sink or settle to bottom of tube, okay, before measuring height more accurately. Because you might get some precipitate on top, but you get some empty layers of the color solution, you know, but your precipitate will eventually sink. You leave it for some time, all of them will sink. So next bit, although the amount of silver halide formed can reasonably be obtained by measuring the height, not reliable. What should be done with the precipitate to obtain a more reliable measurement? How much exactly? So we are more interested in how much exactly AgX is produced. So we are more interested in that. Remember that it is a precipitate and you have a solution, and I said earlier you can filter the precipitate after the reaction. Well, I mean, you stop the reaction already, so filter it, okay? Filter the reaction after the reaction, after precipitate settle at the bottom, after precipitate settles at the bottom of the tube, because before you add the silver nitrate, after you add the silver nitrate, it takes a while for the precipitate to settle, right? But even before you add that, the reaction already stopped, because you already add excess acid to kill all the OH minus, to neutralize all the OH minus. So what happened then is we filter the precipitate. We will when we filter them off, what else do we do? We will dry the precipitate. Dry the precipitate in between filter papers. So that is what you did to obtain dry solid back in O-level or GCSE. We are not sure whether it will decompose or not. Otherwise, you could put it in an oven for drying. All right, and then you gotta weigh the precipitate, weigh the dried precipitate with a mass balance. and because mass balance measures your mass, right? And record the mass of AgX precipitate formed for each halogenal alkane. For each of the 3 halogenal alkane, basically your chloroalkanes, your bromoalkanes, and your iodoalkane. Alright. So last bit is just on hazards. And they did say glove and eye protection are necessary. So you cannot use chemical resistant glove for your answer anymore, because they already say both glove and eye protection are necessary. One other. So you gotta read the question, yeah? And it's only for 1 mark, and that will mark the end of this first question on planning. Well, what's the danger? Did I mention any danger? There is, okay. So they did say in contact with skin and stuff, so you can't use the glove argument again, because they already say other than the glove and the eye protection, which you already have. So you can talk about it's hazardous if you inhale it, so you should do it in a fume cupboard. Or you can talk about the halogenal alkane being flammable. So either of these would have been alright, okay? I'm just going for the flammable, right? But you can go for the harmful if you inhale it, so do in a fume cupboard. So I'm going for the other one. So halogenal alkanes are flammable, which is the other hazard that you mentioned earlier. So keep it away. So keep them away from naked flame. So that refers to any operating Bunsen burner or fire in the lab. Okay, so that marks the end of this first question on planning. In this second question, so you have an equilibrium. So this is your classic NO2 and the dimerization N2O4. So that one is colorless, and NO2 is brown, as you would have known from your group 2 chemistry as part of the decomposition of group 2 nitrate. All right, so it's not something new for you. They want you to work out Kc. So Kc is to do with concentration in a square bracket, concentration of the product to the power of which your stoichiometry says so in the balance equation. So you have 2 there, so your power is 2, and then divide by concentration N2O4 to the power of 1, because there's a 1 in front of the equation. So that's just the expression. Make sure you use square bracket properly. Make sure you know the power is the power to which you raise it to depends on the stoichiometric balance equation. Alright? In this experiment, you have N2O4, which is the colorless gas. You reach an equilibrium which contains some of your reactant and some of this product, which is brown. You want to determine the concentrations of both of these that are present. You get the results in the first 2 columns. So complete the third column to give, well, this is basically this being square, alright? But you need to give it to 3 significant figure. So look at that, that is square. Okay, so grab your calculator and make sure you know it's 3 sig fig. Alright, so you should do this on your own calculator, yeah, because otherwise otherwise you'll find it very tricky in your real deal. And looking at the x-axis, that's alright. Okay, what was I looking for? Oh, I was looking at the y-axis, because you see this is the square term. That's what we're doing. You see how they've expressed it? So on my calculator, the first value gave me like 5.31441 times 10 to the minus 3. But I don't see any of these being expressed as 10 to the minus 3. So I was just a bit curious whether I should leave this as standard form. So I look at my graph, because this is my y-axis, and think about what value they have adopted. It seems like what they have done is they have done where they show all the 0. Okay, so 0.00531, that's the 3 significant figure. Actually, it's another 441 at the end, but 3 significant figure is 0.00531. So the reason I don't leave mine in standard form is because I had a look later on my graph, and we see the value there. If I had left it in standard form, which is correct, it would just make it harder. It would just make it more difficult for me to think about what value to put into the graph. Whereas now, I follow what the graph would have wanted, by going one step further, check out the graph first. I can think about whether I should leave my answer to standard form or in this form. I mean, both will have been equally correct. 472. So this is the last one, 0.000590. That is a lot of zeros. Okay, anyway, so fill in the values, and then you work out the equilibrium constant by plotting this. This is your y, this is your x. And if you look at the expression, you have the NO2 square. That is a bit strange. This is a very strange way of saying it's usually a graph of y against x. Your graph is the squared one. It should have been this here against the x. So actually this is the y and this is the x. There's a very strange way of them putting it. It's always a graph of y against x. So somehow they put the x against the y. Doesn't matter. On the grid, they purposely already give you the correct one. So this is the y. Okay, this is the top bit of your KC expression. There's the one with the square. Okay. So what I'll do is I'll have the table of values somewhere on another piece of paper, and I'm gonna start plotting the graph. All right. So what you need to do is you need to really practice putting in the points on the graph for that 2 marks and see how long you take. Until you could do this very comfortably, you will struggle in the actual deal. Trust me, alright? Practice with at least one. Do a couple more of this graph plotting because it takes practice, yeah? So looking at the axis first, there's 0.00, there's 0.1. So this is 0.05, so each of these is 0.01, 0.02, and so on and so forth. This is 0.001, so this is 0.0005. Okay, so I have a dilemma now because what is each of these, you see? So I have 20 squares. And I have, how many values do I have? 0.001 to 0.000. That is how much division I have for the value. And I have 20 of these squares. So each of the square on the y-axis is actually 0.00005 per square. This is the value per square on the y-axis, just in case if I need it later on. Alright, so I'll start plotting the graph and you can see how long it takes and how long it takes you. Alright, 0.00531 and 0.0729. Oh gosh, I had this value there. 0.0729 is close to 0.73. No, that's not. Okay, I'm looking at the wrong one. The x is 0.9. Sorry, the x is 0.9. So for the x-axis is 0.9. I'm going to draw 0.00531. 0.00531. So that is 531. So that is 0.0055. So that means there is 51, 52, 53. 531 is going to be close to 53, so that is the one. My second point is 0.8 and 472. 0.8 and 472. So that's 45. Well, what I mean by 45 is 0.0045. 472. 0.8 and 47, so that's 46, 47, 472 is somewhere there. and 413 is 0.7, 0.7 and 413. 413 is close to 41. 0.6 and 354. 0.6 and 354. 354 is close to 355. 0.5 and 0.5 and 3. That's the easy one. Let me draw better. 0.5 and 3. 0.4 and 236. 0.4 and 236. 21, 22, 23. 236 is close to 235. So there's 21, 22, 23. There's 235. So that's where I put my point, yeah? Go for something which is close to it. 0.3 and 152. There's 15. 152 is close to 15. 0.2 and 118. 0.2 and 118. 1, 2. 118 is close to 12. 0.1 and, oh, this is a really small one. 0.1 and 59. 59 is close to 60, so it's there. And you can imagine you don't have the point at origin, but what does it mean when x equal to 0? When there is no n2 or 4, that means 0. When there is no n2 or 4, when there is no n2 or 4, can you get NO2? When there's nothing, then there's no dimerization, there is no equilibrium, then there's no NO2. When there is no n2 or 4, there is no NO2 being produced. The NO2 concentration score is going to be 0. So we know this graph will cut through 0, 0, but we don't put a cross there because we only put a cross for the points on the table. But we think about whether you'll cut through 0, 0 or not, in the sense that think about what happens when x equal to 0, okay? So I'm going to try and draw my graph now. Nope. You should have a ruler, yeah? You always have a ruler in a science practical exam. So I think that is so you use a ruler and you can see that is not good, that is better. This is not good. A lot of the points don't lie on the line. This is probably the best I could do. Alright, and out of all the points that lie on the line, this is the only one that's out. Alright, I can tell this is very clearly out, and I have a feeling that they will ask me about the anomalous point later on. Anomalous being out of ordinary, okay? Have I completed everything? Yep, okay. And yeah, see how long that took me and see how long that takes you, yeah? So it turns out that I don't really need this. It turns out to be quite easy to read them, so not really that useful here, but there are other cases when they are useful. Actually I keep them, okay? Since I already done them anyway. Now choose two sets of values from your graph, not from the points, okay? Calculate a value for the equilibrium constant and give your answer to 3 significant figure. They want you to use your graph to calculate equilibrium constant. Remember just now you have Kc is equal to your NO2 square over your, what was it? NO2 square over your N2O4. So that is your, so if you have NO2 square, it's equal to Kc times N2O4. So I hope you can see that is your y-axis, that is your x-axis, that is your m, your gradient. Usually we have plus constant, okay, but there is no y-intercept, which is your constant, because what happened when x equal to 0? When there is no N2O4, there is no NO2, there is no NO2 square, alright? That's why there's no y-intercept there, alright? That's why there's no constant there. So that means from your coordinate, you can work out gradient. Okay, so that is the relationship there. Rearranging it, then you can get the y equal to mx relationship. I can see it pass through 0, 0, so that can be my one coordinate, but I cannot use it if I do not show the line going through that point. I do not extend it to negative because there's no negative concentration, alright? But because I show the line extending to this point, so I can use 0, 0 as my coordinate. So 0.00 and then 0.000. Follow the graph. And the other value is I can use this one, okay, not the point, not the cross, but where it cuts exactly here, where the line cuts, that is 0.90. So 0.90 on the x, and this is, what is this? This is 0.0055. So 2 of it is 0.0054. So that is 0.00535. Because there is 54, this is 53, so this is in between, you know, where the line cuts through the 0.90. So that is the value there. I'm just going to copy that because I don't want to remember things when I can just, you know, flick your pages back and forth, which, you know, you do have the actual paper in the real deal. Okay, use your bracket because a lot of students they struggle with using bracket somehow. So I get 5.35 times 10 to the minus 3 divided by 0.90. It's very obvious that this will be a positive gradient because even your graph earlier was a positive slope. So I'll get 5.94 times 10 to the minus 3. There's 3 significant figure. And they want the units. Well, at least to give you another 1 mark. This one is mole square dm minus 6. So your y-axis is mole square dm minus 6. Your x-axis is mole per dm cube. Mole per dm cube. Okay. So your final unit is going to be mole per dm cube. Essentially the top bit is mole per dm cube, the whole thing square. Like that. That will give you mole square dm minus 6. When you divide that by mole per dm cube, that is the power 1. They cancel out. Okay. And they just give you mole per dm cube. And your value to 3 significant figure is your gradient to 3 significant figure as required. Okay. Identify the result, most anomalous. So there's only one. It's singular. Okay. When they say the result, there's only one. Identify it. So which one is it? It's the one that I've circled. It's the value at 0.30. It's the value at 0.30. Okay, it's the value for N2O4 at 0.30. So it is the 0.4 N2O4. Your x-axis equal to 0.30 mole per dm cube. Alright, so what can we say? Is the point above or below the line? It is lower, it's below the line, it's lower than expected. Okay, so what is lower? The y-axis is lower than expected. We expect it to be there. For that x-axis value, it should be there, but it is lower than expected, and that is your NO2 square. Alright, the NO2 square value is lower than expected. Is below the line, which is lower than expected. It's below the straight line plot, therefore lower than expected. So we have this equilibrium earlier, right? This going to 2 NO2. We have the reading of this at 0.30. So what is the concentration of NO2, right? So lower than expected, therefore NO2 also lower than expected. So you get the square from this at first, yeah? So that one also lower than expected. So you need to think about what can cause your NO2 to be lower than expected, alright? If you look at the graph, this value of the y-axis, this value on the y-axis should have been there for this thing, should have been for a lower concentration of N2O4. That will give you this particular y value. But when you go higher N2O4, you should get a higher y-axis value, but instead you still get the same one. So meaning to say, you must have recorded the reading at 0.30 a bit too early that you are recording for a lower concentration of N2O4. That's why your reading on the y-axis is a bit lower. Okay, you must have taken the reading for a lower concentration of N2O4. So must have taken the NO2 concentration. So in a square bracket is concentration reading at a lower N2O4 concentration. And what do I say? So and must therefore have been taken too early. Okay. Well, too early, that means before your equilibrium already been established, you already took the reading. So you expect the equilibrium to go a bit further and give you a bit more of this, but you have taken the reading a bit early. Okay, so it hasn't reached all that value yet. Of course, what else can we say? This reaction is at 25 degrees. So, well, temperature can change your equilibrium position, right? So, when you take this reading, you have lesser NO2. You have lesser NO2. Why is it you have lesser NO2? You have lesser NO2 because the equilibrium favors that way. So we could say no, I don't want to go that path. It's probably a bit too complicated. Okay, let's just leave it a bit easy and straightforward there. All right. So next bit on your graph, draw a line if the temperature was raised. Okay, if you increase temperature, what would happen to your graph essentially? Okay, so if we think about what will happen first, if we just explain first, so I'll come back to this. All right, so we know the forward reaction, we were given the enthalpy change of the reaction, so I'm going to refer back to it. There is the forward reaction is endothermic. So the forward reaction is endothermic. So it absorbs heat energy from the surroundings. So higher temperature means the system or the reaction will absorb more heat. Therefore, it will favor forward reaction. It will shift equilibrium to the right. And when you shift equilibrium to the right, remember your equilibrium was N2O4. Was it N2O4 going to NO2? Yep, it was N2O4 going to NO2. When you shift to the right, you will get more NO2. Therefore, more NO2. Alright? Your gradient is basically concentration of NO2 against N2O4. So we know that equilibrium constant Kc increases with increasing temperature because this forward reaction is endothermic, because only temperature can change the value of Kc. Alright? So because you favor more to the right, you get more NO2. Temperature change can cause a change in Kc. Because you get more on the right hand side, your Kc will become more positive. Your Kc is your gradient. So the line that you obtain at a higher temperature for this reaction, which is endothermic in the forward reaction, so we will expect the gradient to be more positive. So I could draw a line. So it will still does not matter really. Like, as long as I show more positive gradient, that should have been alright. So that one is for higher temperature. Higher temperature. Okay, of course you don't use colored pen, you don't use colored ink apart from blue and black in a real exam, so you just have to label it. Do I know the exact value? No, I don't, but it is a line. When there is no N2O4, there's no NO2, so it still start from 0, 0. It's a more positive gradient because the value of Kc increases with temperature, because the flow reaction is endothermic. So I think the next part is, what would the higher temperature do on the value of Kc? I think I have put it in the previous question, so what I'll do is I will move that over here so that I don't have to write it again, but it seems I've moved something else as well. Favor forward reaction, it will shift equilibrium to the right, and therefore your Kc can change with temperature, so your Kc will increase with temperature for this particular reaction. That's why we drew the line with a more positive gradient, because the gradient represents Kc based on this relationship that was given in this Kc expression. So how would your value for equilibrium constant change if you apply pressure? There will be no effect or no change, because equilibrium constant value is only affected by changes in temperature based on Le Chatelier principle. Okay? This is the last question of this paper 5 tutorial. So in the experiments, you have started with pure N2O4. Start with pure N2O4, and then you let equilibrium to form the NO2. So they want you to work out the starting concentration of pure N2O4. So let the starting concentration of pure N2O4 gas be X. You have N2O4 gas. So this is the last question. They involve a bit of calculation. So it's not really mean of them, alright, because it's towards the end of the question, so that's fine, yeah. So instead of mole, we start with concentration. We have X, we have nothing, and then at equilibrium. At equilibrium, we have 0.900, and we have 0.0729. All right. So looking at the equation, I hope you can see that the mole of NO2 form relative to the mole of N2O4 reacted. Okay. However much you form, it comes from whatever much that has reacted. You form 2 mole of NO2 from 1 mole of N2O4, alright? So how much of it that you actually reacted? So the mole of NO2 form is 0.0729, because you start from 0 to that. So that's how much you have formed. I have ignored that this is mole and this concentration, partly because the total volume is the same, so you can multiply by a constant volume. Bottom bit multiplied by constant volume. The constant volume can get cancelled out, alright, to give you the mole. So how much N2O4 actually reacted is based on this ratio. I've been very careful to label it as being reacted, because a lot of students, they struggle with equilibrium question because they just don't label. When you don't label your thing, you get confused between what has reacted and what has been formed, right? So I just work out how much of the N2O4 had reacted. So this one is minus what has reacted. Then you have this much left at equilibrium, okay? So therefore, X is equal to whatever you have left at equilibrium plus whatever that has reacted to give you the product. So 0.03645. I get this as the exact answer, but that is to too many significant figures, whereas the data was only given to 1, 2, and 3. 1, 2, and 3. You need to think about appropriate number of significant figure, because this is stated all the way in AS specification, topic number 1. I think it says candidate must know when and what to do with appropriate number of significant figure. The unit here is mole per dm cube, because they were specifically asking for starting concentration. All of these were in mole per dm cube. So that's the end of this paper 5 tutorial.